Hello, myself Prasant Mukhopadhyay. In the last class, we have discussed about the single layer winding in the fundamentals of AC windings uh, portion. Now, today we'll discuss a double layer winding. So, double layer winding has identical coils with one coil side of each coil lying in the top half of the slot and the other coil side in the bottom half of the another slot. And this another slot is exactly or approximately one pole pitch apart. See, this is the portion is shown, this is the top half, this is the bottom half. So each layer may contain more than one coil side in case of large number of coils are required. So this is shown here, this is top coil side of the top layer, this is bottom coil side of the bottom layer. And this arrangement shows where 8 coils, see, in the top of 4 coil side and at the bottom another 4 coil. So 8 coil sides per slot. So this is open slots are frequently used to house double layer winding because it is you know it is if it is a semi-closed type slots, so it will be difficult for inserting this double layer 8 number of coil sides in a particular slot. So that's why frequently it is used open slots. Okay. Now, what is the advantages of this double layer winding over single layer winding? So before discussing, once again I am telling you, so in case of single layer winding we have only say one coil side in one slot. It was given in the earlier class. I have shown you. So this picture once again I am showing. So this one, so this is semi-closed, this is closed, and in double layer, you know, in each slot there must be 2 layers. This is for top layer, this is bottom layer, and if it is this top coil sides, bottom coil sides, and definitely bottom coil sides of another coil. Okay. So what is the advantage? See, this is 8 coil sides per slot. Now, what is the advantage? Now, advantage is easier to manufacture and lower the cost of the coils. And secondly, fractional slot winding can be used. And thirdly, corded winding is possible. So lower leakage reactance and therefore better performance of the machines. So that's another thing. So lower leakage reactance means so lower leakage reactance shows the better magnetic path and magnetic MMF actually. So better EMF waveform in case of generator. Better MMF means better magnetic path means better EMF waveforms also. Now, mostly in armature winding, separate coils may be connected in several different manners, but the two most common methods are lap and wave. You know, once again I am telling you the most common methods for armature windings are lap winding and wave winding. Now we'll discuss. Say in polyphase windings, so it is essential that the generated EMFs of all the phases are of equal magnitude. This is essential. The generated EMFs of all the phases are of equal magnitude. Waveforms of the phase EMFs must be identical, and the frequency of the phase EMFs are equal, and phase EMFs have mutual time phase displacement. beta equal to twice pi by m electrical radians, and m is the number of phases of the AC machines. Mostly we are using the 3 phases. Some other special, like say applications, more than 6 phases are also used. Now for this, with this essentials of polyphase windings, we will come to the point of say number of phases and phase spread. So basically this is obtained having similar pole phase groups. That means a pole phase group can be defined as a group of coils of a phase under one pole. Pole phase group, that is group of coils of a phase under one pole, and arranging the groups to have an effective displacement of twice pi by m electrical radians in space. So to get it understand in a very U-shaped and understandable manner, so we'll consider case of 12 slot armature having 2 poles and one for 3 phases. 12 slot, 2 poles and one for 3 phases. So that is shown here in this figure. So if the flux density wave shape is considered sinusoidal, the EMFs of the conductors of the slot can be represented as a phasors displaced from each other by an electrical angle. Will be how much? It will be pi p by s, where pi is say p is the number of poles, s is the number of slots. Then if you put here p equal to 3 and s equal to 12, it will come to 30 degree, pi by 6 radians. So this is the arrangement shown here for 3-phase winding of space spread. Definitely 120 degree, because you know how we are getting 120 degree. If the winding is divided into 3 groups, that is one for each phase spread over 2 pole pitches, the electrical displacement in space between the groups will be how much? This will be twice pi by 3 electrical radians, or it will be 120 degree electrical. So this arrangement is here shown here. So this is one phase spread, another, this is another. So each phase is located in 4 consecutive slots, and so the phase spread is 4 into 30 degree, that is 120 degree. This is 30 degree, 30 degree. You will get 30 and 30. Okay, so 120 degree. So you will get for 4 conductors. If the conductors in the slots are connected as per the phasor diagram, this is given figure 7b, the summation of the conductors EMFs would give the 3 EMFs displaced by 120 degree. This is the summation. This is conductor 1 EMF, this is conductor 2, this will be conductor 3, and this is conductor 4. So in this way, this is for A phase, this is for B phase, this is for C phase. And see, you know, this phase difference is 120 degree, this is 120, this is 120 degree. So this is the total EMF, okay, of this one phase kit, 4 conductors. So this is the time phase angle of this between EA, EB and EC is 120 degree from each other. So that's all about this phase spread. For once again I am telling you, once again I am repeating this we let me consider the 12 slot armature. So there are 12 slots here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And 2 poles. You know, 2 poles and wound with 3 phases. The phase A, phase B, and phase C. So the flux density wave shape is considered sinusoidal. Then EMF of the conductors in the slots can be represented as a phasor displaced from each other by an electrical angle by 30 degrees. This only. So this is 30 degrees. 30 degrees. Okay. So because you know, if winding is divided into 3 groups, that means 1 for each phase, spread over 2 poles. These 3 phases spread over the 2 poles of the machines. Then the electrical displacement in the space between the groups is how much? It will be 2 pi by 3 electrical radian or 120 degree electrical. Then so we can write each phase is located in 4 consecutive slots, and so the phase spread is 4 into 30. Okay, 4 into 30, that means 120 degree electrical. So if the conductors in the slots are connected as per the phasor diagram given here, like this. Okay. So EMF, the summation of the conductors EMF, this is for conductor 1, EMF E1, this is for conductor 2, EMF, this is 3, and this is 4. So this is the resultant EMF, and this is for phase A. Okay, the summation of the conductor would give. So this is for phase A, and this is for phase B. So 5, you know, if you go here, this will, you see 5, 6, 7, 8 for phase B. So if you see, this is for EMF for conductor due to conductor 5, this is for conductor 2, 6, 7, 8. So sum of this EM, E5, E6, E7 and E8 will give you the EMF of the phase B, EB, and this is 120 degree apart from A phase EMF. Now for conductor C phase, this will be, you know, in C phase you have how much? 9, 10, 11 and 12. These are the conductors. So if you sum up here, this is E9 due to conductor 9, this is for conductor 10, this is conductor 11, this is conductor 12. And you see each EMF say 30 degree apart. Okay, so this is the resultant EMF of the phase C. This is EC. Okay, so now you see, so this EC is again, say it is out of phase from B of 120 degree. So you know the space sequence. So this time following a phase sequence of ABC in time, and the space sequence is also ABC, A, B and C. So with this example of say 2 poles, 6 slots, 12 slots, 2 poles, 3 phase machine. So this is the phase spread, and it's the time phase angle between the 3 phases EMFs. Okay, so that will clear you your idea about this phases and phase spread, and you must be guided to draw this with the essential polyphase windings tip. terminology. Now we'll discuss winding is split up into six 60-degree phase groups spread over two pole pitches, so that as shown in this figure. So you see, this is a three-phase winding. Phase spread is 60-degree. In that case, in last class we have in the last discussions we have seen of three-phase of 120-degree phase group. Now we consider into 60-degree, six 60-degree phase groups. So this is the actually phase spread in 60-degree. Here you see in phase A, conductors are placed in slots 1, 2 and 7, 8. Okay, this is for phase A. Here, for phase B, conductors are placed in slots 5 and 6, and then it will return path is 11 and 12. So conductors of phase C are placed in 3, 4 and 9, 10. Okay. Conductors in slot 7 and 8 are return conductors for, as I told you, for 1 and 2. And similarly, conductors in slot 11 and 12 are return conductors of 5 and 6. And conductors in slots 3 and 4 are return conductors for slots 9 and 10. Okay, let's see. So now if the conductors are connected as represented in this figure B, you could still get three equal EMFs displaced by 120 degree. Okay, in the space sequence. Here ABC. The space sequence in that case will be how much? It will be A, C dash, B, A dash, C, B dash, A. Okay, this will be the space sequence. I told you A, C dash, B, A dash, C, B dash. Thus, it is clear that with six 60-degree phase groups, 3 60-degree groups per pole, spread over pole pitches, it is possible to obtain 3 equal EMFs displaced 120 degree in time, and that is shown here. This time phase diagram. This is the time phase diagram for the EMFs generated in space spread of 60 degree 12 slots to pole winding arrangement. And you see here, this is the generated EMF for conductor 1, this is for 2, this is for 3, this is for 4, 5, this is 6, this is for 7, this is for conductor 8, this is for conductor 9, this is for conductor 10, this is for conductor 11, this is for 12. And that is shown here. Okay. See, you know, if phase A having 1, 2 and 7, 8. This is say forward part, this is return part. Okay, here. This is for say B, this part, this is return, and for C also. So this is. So actually in this way we are getting 6 60-degree phase groups, and which in the EMF will be of course of 3 phase with say 120 degree apart in phase sequence of ABC. Okay. Now We'll in short discuss the types of single layer winding. So if one coil side occupies one slot completely in once are completely in view this, the number of coils C is equal to the half of the number of the slots. In that case, C will be S by 2. And for three most common type of single layer windings are uh, concentric windings, it is of unequal coil span. Then chain windings, that is of equal coil span, and Moose windings, that is also again of equal span. So this is a single layer winding types. And for double layer winding, say synchronous machine, armature, and say and induction motors above a few kilowatt are owned with double layer windings. If the number of slots per pole per phase equal to S by MP is an integer, then the winding is called integral slot winding. In case the number of slots per pole per phase Q is not an integer, the winding is called fractional slot winding. Suppose an example of three-phase winding with 36 slots and 4 pole is an integral slot winding because Q equal to 36 by 3 into 4, that is equal to 3 is an integer. But if it is a 30 slots and 4 poles for three phase, so it will be 30 by 3 into 4, that is equal to 2, it is not an integer. So if the number of coils C is always equal to the number of slots S, that's equal to C equal to S. So that's about double layer winding. Okay. Now we'll show you some pictorial view. So this is the armature of the stator winding for distributed one. This is the armature, this is the slot, this is the armature coil, this is phase. So this is, if it is forward, it is return conductor. So in this way. So this is the coil span. So this is for stator winding distributed. And now this is this arrangement for rotor winding, concentric winding. See, this is the rotor winding. Here, concentric winding. Okay. Now, what will be the complete proposed machine's 3D view? This one. This is armature stator. This is rotor. So that's all about your in an nutshell about say fundamentals of AC windings. And with this, we'll show what we find in this class. That is, if we summarize the say previous lectures and everything of today's lectures regarding this AC fundamentals of AC winding, what we got, we have seen say different terminology for in a quick what are the different terminology used for AC windings, what is turn, coil, coil side, conductor, overhang, then types of windings, then what is coil span, what is coil speed, and how the conductor is a coil is defined as a short piece or full piece. Then we got types of AC machines winding, single layer winding, double layer winding, their advantages, disadvantages, how they are say look at. Then we come to their advantages over one another, and where single layer winding or double layer winding is used, and what are the essential to remember for say AC windings for polyphase. Then we come to the point of phases, phase spread, and with two examples actually, we have taken one for 12 slot, two poles, three-phase machines, how the conductors are spread over the periphery of the armature, and how the EMF is being generated, and how the EMF per phase is being summed up for each conductors, and then how the phase sequence of the generated EMFs and the phase difference has been created. We have seen. Then again, we have taken another one example, that is same say 36 slots, 12 slots, sorry, 12 slots, 6 group, 60-degree electrical effort, say 60-degree phase groups, spread over two poles pitches, and how the conductors is being say placed in different slots for different phases for forward and return conductors. There is shown how the EMF induced EMF for per phase, and how the contributions for each conductor for in a phase groups are coming out. It is shown here also. And then we have a short discussions about single layer winding, how many types of single layer winding, what is the concentric winding, chain winding, bush winding. Then we go through double layer winding, what is the integral slot winding, fractional slot windings, etc. And then there say when it is called say integral slot and then winding, when it is called fractional slot. We have taken an example of three-phase 36 slots and four-phase machines. We are find that integral, what is when it is called integral slot winding, when it is called fractional slot winding. If slots are 30 slots on the same four poles and three-phase machines, will be fractional slot winding. And at this point, it will take into consideration remembering this C equal to S, is number of slots, and we have some pictorial view of the arrangement of the stator winding, distributed winding in a machine. See, and then we have gone to rotor winding, concentric, okay, and taking into consideration both these armature, say stator and rotor, what will the how the three-dimensional 3D diagram the focus machine will be. So this is for the stator part, and this is for the rotor part. So this is once again I'm telling all about this fundamentals of AC windings, and after studying this, if you have any problem, I told you that you can contact me over my email or mobile number or my WhatsApp number. So in that case, we can discuss whatever we can try out with the problems you are facing to sort it out, and that's all about this class. I personally thank you all for listening and give your say patience hearing of this class. So thank you all very much. Okay.